In this lecture, I'll discuss hypothesis testing for cases in which the normal distribution can be used. Okay, we can use this normal distribution if certain conditions are met. We're going to assume that the a priori value is the mean of a certain population, and that the data that determined this mean, we also from that data know the standard deviation. Or the sample size is large. So what are we talking about here? Okay, here was your a priori values. Its value was mu naught, but this mu naught was determined from some study, and from that study we also know its standard deviation. Okay, then we have some new measurement, and I'm going to call that, I'm going to put it in here for, well, I'll put new for here. This is my new measurement. Now when I write the hypotheses, H naught, it's going to be that the mean is still my previously measured mean, and that the alternative, I'll just say it's a two-tailed test, is that the mean is no longer equal to mu naught. Okay, now the study that developed this new value had a certain number of, that's an n, certain number of, there's a certain number in the sampling, okay, and also it would have a standard deviation associated with it. Okay, so let's go over this again. The idea is that you have a study that was done a long time ago, and it gave you a mean. You took this mean and used it in your null hypothesis right here. Well, it also appears in the other one, but let's just say it, let's look at it that way. Okay, that original study also had a standard deviation associated with it, and you know that. All right. Now when you do the new study, you get a new value for the mean. Or this is the mean for the new study. That study had a sample size of n. It also has its own standard deviation of s. Okay, now in order to use that normal distribution, n has to be large, and we aren't going to go into what constitutes large, but n has to be large, obviously greater than something like 5 or 3. Okay, in that case you can use this standard deviation as opposed to this one. So in that case you didn't really have to know this, and that's what the and or means. So you have this mean of a population that was measured in the past, and either or you know the standard deviation is sigma, or the sample size is large. Now in that case we're going to use z values and the normal distribution. So the first thing I'm going to do here, the first thing that I show, is that this new value has to be changed into a z value, and it's done in the usual way. I should have put an in here. So you take the new value minus the previously held value and divide it by the standard deviation for the population divided by the square root of n. I'm going to say something about that in a minute. Or, because the sample size is large enough, you can replace this population standard deviation with the standard deviation of the study. That was a lot of words, but here's something that's I need to talk about. This is a compound or complex fraction. What's in the numerator? Let's say it's 3, and in the denominator is, we'll say, 2 divided by the square root of 25. Okay. If you're not careful when you try to calculate something like this in your calculator, you will end up doing 3/2 and doing something like that. The square root of 25, which of course is just 5, will end up multiplying the 2 if you do it wrong. You can also do it wrong in z. What does this really mean? Okay, what this means is 3, and then in fractions, as you know, that's really divided. So this means 3 over 1 divided by 2 over the square root of 25. Okay, let me erase some of the board here for a second. Well, okay. So if you are remembering fractions, I leave this alone, change this into a multiply by putting this thing, taking the reciprocal there. Now that's really the problem. That's really what's going on. Okay, it's written like this because the idea of putting important variables together, and it's correct, but there's sometimes students do it wrong. Now how can you do this right on your calculator? Just using this example, if you've got the Casio calculators that I like, and I'm sure the graphing calculators, you can write in the equation using parentheses, and if you do the parentheses right, you're okay. Remember that not all computer programs or calculators obey the laws of PEMDAS. So even though you write it a way that is correct according to the algebraic idea of PEMDAS, it may not come out the way that you need it to. However, all of them respect parentheses. So if I put 3 here, and then I put divide, and now if I put parentheses, and I put sigma, which was 2, divided by, I'm putting the square root of 25 just so you can have a number to look at. That will work out. If you go 3 divided by 2 divided by square root of 25, the results are not, you aren't sure what results you're going to get. This is true in R also. If you want this calculation to be done like that, put it in parentheses, and then the calculator or the computer will obey the parentheses and give you what you need. Now you can just sort of hold that calculation in your back pocket for a minute, and let's set up the critical values and the critical regions. So we'll do it with an example, which is probably easier to do than a lot of words. So let's say a long time ago the World Health Organization measured 1.5 zillion 4-year-old girls and said that their heights were normally distributed with a mean of 102.73 centimeters and a standard deviation of about 4.3. Okay, you can even look that up and find out that's real data. All right, so here was your situation right here. Their mean was 102.73, standard deviation of 43.07. Okay, now you get some new research in here, and the new research says that the mean height is 103.601 instead of 102.73 for a group of 34-year-old girls in the US. So let's see how we're going to write that as null and alternative hypotheses. Okay, so the null hypothesis says that the mean height, which I'll just write as mean, is equal to the previously determined value of 102.73. The alternative hypothesis, because this is greater than, it could be written as greater than 102.73, but to get a two-tailed test, just for example here, I chose not equal to 102.73. This is going to be a two-tailed test. Because it's not equal to it, this would have been a right-tailed test. So we've chosen here an alpha of, whoops, supposed to be a marker here, an alpha of 10%. That means that the goal is a 10% probability of making a type 1 error, or 90% confidence that by accepting the null hypothesis you'll be doing the right thing. Okay, so if it's a 10% and it's a two-tailed test, then the area in each tail is half of the 0.1, which is 0.05. So now, in this case, I just looked up the critical values. So here's what I'm looking at. I have this deviation like this distribution here, and I want to be two tails symmetric about right here, and I want the area in each tail to be 0.05. I need to know the value right here at the edge. That's my critical value. You can look that up, okay, or I'll show you how to get it from R in a minute. So this critical value turns out to be 1.65, and down here of course it's going to be minus 1.65. Okay. Now we're using here the Z's, so the standard normal distribution, so I need to change the new data, the new mean, into a Z value to see whether it falls in the non-critical region or in the critical region. So here's the calculation for Z. Okay, it's going to be the new value, which is 103.601, minus the old value, divided by, in this case, the standard deviation of the population, because I knew it, which is itself divided by the square root of the size of the sample, and the size of the sample was 30. So they gave me 1.1074. Okay, 101.74 is, there's a better picture in a minute, but since I'm talking about it, I'll just write it here. It's here. Okay, well, it's not in the critical region. It's way over here in the non-critical region. Therefore, the null hypothesis is not rejected. And here's a nice graph showing that result. So we had an alpha of 0.1 in a two-tailed test. So the area in each tail is 0.05. The critical values are symmetric, and they are the values of Z right at the edge of the critical region. And in this case, 1.65 and minus 1.65, they are symmetric. The test value came in at 1.1074. Forget the K, that was from a lecture, previous lecture, and you can see that it lies close to the mean in the non-critical region, so the null hypothesis in this case is not rejected. Okay, and the confidence of making the type 1 error is of not making the type 1 error is 90%. Obviously, you can change the probability to, well, actually any value you want. So there's your two-tailed test for normal distribution. So let's just go through here for a left-tailed test. Okay, for the left-tailed test, let's say you have the average weight of a sack of potatoes, 5-pound sack of potatoes, is 4.9 pounds with a standard deviation of 0.47. Right. So then you get a sample of 50 sacks of potatoes and weigh them to see if the sacks are getting lighter. And the mean from the testing was 4.4. Remember, it was 4.9, now it's 4.4. So it's less than, so we're going to write it for a left-tailed test, meaning that the alternative hypothesis is written as mu is less than 4.9. So again, we use the 10% probability of making a type 1 error. So alpha is 0.10, and the area under that left tail is going to be 0.10. Okay. And you can find this critical value here from the tables, and I keep promising to show you how to do it in R in a second. Now, the test value, which is 4.4, needs to be converted to a Z-score. Here's that calculation from before. You're familiar with it, and you come up with minus 1.67. This is obviously further in to the critical region, and so the null hypothesis in this case would be rejected. And here's a graph of the situation. So again, we've gone to using Z values. Alright. And the previous mean was transferred into, so this is your mu naught, which previously was 4.9, but its Z value is 0. Okay. After you choose your confidence level, or whether you're alpha, then you can find It means this area has to be 0.10. You can find the critical value, which we used to call Z alpha. We used to call Z alpha over 2 because we always had two tails, but here we can have one. So this is just, they don't use the Z alpha, but it's just what previously was, I just mentioned it for that reason. But now the critical value, which is really a Z value, right at the edge of the critical region is minus 1.28. Now you have your test value in terms of Z is minus 1.67. As you see, that measurement is over here in the critical region. Therefore, the null hypothesis is rejected. Now let's look a little bit on how to do this in R. And what you really are interested in finding is the critical value. All right, let's do it for the case of Z. So we're working in the Z, in the standard normal curve. All right. Recall previously we had, for this is normal distribution, we had this base word norm, and if we did denorm, we got the distribution. That would be, we could get the points along this curve. Okay. When we use p-norm, we got the probability because we were getting the area under the curve. And we had a chance here with the p-norm, certain parameters, it's to say lower dot tail, lower dot tail equals false. If we left it alone, the default is lower dot tail equals true. If lower dot tail is false, then we're going to get the area to the right. If we leave that off, we get the area to the left that's under the curve. Right. So for denorm, we're specifying these Z or X values, and the program is returning the points along the curve. Okay. For p-norm, okay, we're specifying again a Z value, and we're getting the area to the right or to the left of that Z value, the area under the curve, which is the probability. Now that what we're going to use here is Q-norm, and this is in the tutorial for R. And for Q-norm, what we do is we give it the area, and it gives us back a Z value. So let's say you give Q-norm an area of, I don't know, 0.3, and that would mean you'd be telling R that you want a tail well, 3 is a little bit high, isn't it? I put it at 0.3. That has, you want this area to be 0.3, and you want to know the Z value that's right at the edge of that area. If you tell it Q-norm, and you're going to specify some parameters, and then you go lower dot tail equals false, then you want to find the Z value that would be on the edge right up here. Okay, so what is this giving you? This is giving you the critical values that you need for your hypothesis testing. What's really handy here is that for R, you aren't stuck with Z values. For this distribution, you can specify, for example, you can go Q-norm, and let's say the area that you want is 0.3. You can say mean equals 100, whatever it is. Standard deviation equals 2.75. Lower dot tail equals false. Remember, the default is true. Okay, what's this going to give you? You didn't have to change anything into Z values. It is for a curve, I'll just use this one here, with a mean of 100 and a standard deviation of 2.75. If you say lower tail equals false, you're going to find the area up here for this particular curve. You're going to find the Z value here, and it's not going to be it's not going to be the Z value. It's going to be the value from this, from this scaling of the normal distribution, so that the area under the tail to the right is 0.3. Okay, let's say your alpha is, well, let's give it something 0.05, because the confidence level you want or require is 95%. Okay, so for a two-tailed test, you would issue the command qnorm, and then you only want to give half this area. You could write it as a over 2 if you have this signal, depending how your variable is specified, or you could go 0.025. All right, and it's just as handy to say lower dot tail equals false, except L usually goes before S in false. Okay, and this will give you the critical value on the right hand side. The critical value on the left hand side is just the negative of this critical value. I can put an R here because it's symmetric. If you left lower tail equals false off, you would get the negative one, and you just have to, of course, change the sign to get the right. Now if you have a one-tailed test, and let's say it's a right tail, all you need is the right critical value, qnorm, but in this case you don't divide by 2, so you would give it 0.05 for that complete area, and it's right, so you want to do lower dot tail equals false. Okay, for a one-tailed test, that's a left tail. It's similar, except you leave off the lower dot tail equals false, or you could say lower dot tail equals true if you just want to write it out. In these cases, we were using the standard distribution, so you have to change your test value into a z-value, and like I said, you can do that right in R. And if you look at the R tutorial under hypothesis testing, it shows how to do this.